My name is Joe Vesta. This is Math 265A, and we are doing 3.11 related rates. Before I get started, I want you to call your attention to this. This is Derivative Rules, which is a PDF that you can find on my website. So there are some derivative rules. The ones below that little shaded area are ones you really wouldn't have to memorize, but the ones above, you do want to commit them to memory. Okay. So what we're going to do is we're going to start something called related rates. We kind of break this into three parts. The first part happens to be the next few problems. So let's try this out. Differentiate with respect to t. How many variables are in your answer? Well, we've always been differentiating with respect to x in a lot of our class examples, but there are no t's in this. The first thing is to realize that t is usually going to stand for time when we do related rates. So when I differentiate with respect to t, d dt of both sides of this equation, I differentiate with respect to t on this one. The derivative of z is 1, and then we have dz dt. So 1 dz dt. So this might remind you of when we were doing implicit differentiation. I'm going to take the derivative of x squared. Normally we would just say 2x and leave it at that because we have d dx, but this is d dt. So 2x, then we'd have dx dt. And then plus derivative of y squared is 2y dy dt. And so this gives us our answer, really. Let's go ahead and box this without the 1 in the front. Differentiate with respect to t. Now they ask, how many variables are there? It looks like there's 3 variables, but really what we have for our variables is the x and the y. That's 2 of them there. But other variables in this equation here would be dy dt. That is a variable. That's the rate of change derivative of y with respect to t. So that right there is a variable, and same with the dx dt and the dz dt. So I'll count them. 1, 2, 3, 4, 5 variables. And so that answers that question. Let's go ahead and do another one that is similar. We are differentiating with respect to time. So I'm going to go d dt, or with respect to t, x squared y cubed. Okay, just rewriting this. So the derivative of this product, we're going to use the product rule. The product rule says the derivative of the first 2x, and then you have to put a little marker here, dx dt. That's the derivative of the first. Now remember, this is with respect to t, times the second, plus the first times the derivative of the second, 3y squared, and then dy dt. This equals the derivative of sine x, which is cosine x, times dx dt. So this should remind you of implicit differentiation. With that we were differentiating with respect to x. And when that happened, we did not put an extra dx dt because it was dx dx. Let's write out our answer so it looks nice. 2xy cubed dx dt plus 3x squared y squared dy dt. This equals the cosine of x dx dt. So the first part said differentiate with respect to t. The second part says how many variables are there. Well, let's count these derivatives first. It looks like there's 3 of them, but this one is the same as that one. So we have dx dt, dy dt. That's 2. And then the x and the y that you see throughout the equation. So that's going to be 4 variables. And if you're wondering what they are x, y, dx dt, dy dt. And I don't see any other variables within that equation that I have boxed. Okay, let's go ahead and do another problem. This one's a little different. Assume x and y are functions of t. Let xy plus x squared equal 15. Find dy dt when x is 3 and dx dt is 5. So this looks really weird. What we want to do is differentiate both sides with respect to t. See, you have these dt's on the bottom, and they say they're functions of t. So I'm going to go ahead and do the product rule. The derivative of the first, 1 dx dt, times the second, plus the first, times the derivative of the second. The derivative of the second, the derivative of y is 1, and then we have dy dt. And yes, I did an obvious mistake here. I wrote down the equation incorrectly. There's an x squared there. Okay, so there is the derivative of xy. The derivative of x squared is 2x dx dt. And the derivative of a constant, 15, is 0. Okay, let's write this out nicely. Y dx dt plus x dy dt plus 2x dx dt equals 0. So now they're giving us some values here. They're telling us that x is 3. So we can put a 3 there. They're telling us dx dt is 5. So we can put 5 there. We're trying to solve for this, dy dt. And there's also a y here. So what do we do about that? Well, we can find the value of y because we know what x is. And what we're going to do is we're going to put the x equals 3 into that equation. So I have 3y plus 3 squared equals 15. 3y equals 6, y equals 2. So we can put the 2 right there. Now some teachers would say before you start plugging the values in, solve for the dy dt. You can do it either way. I'm just going to plug those values in where we see the colors. So this is 2 times 5 plus 3 times dy dt plus 2 times 3 times 5. Whoops, what happened to my 5? Using that white out a lot today. This equals 0. Okay, so what we have here is, we're running out of space. 10 plus 3 dy dt plus 30 equals 0. Bring it up here. There's 40 that I'm going to subtract, so I have 3 dy dt. Just treat that as a variable. Dy dt is just one thing. Equals negative 40 dy dt is negative 40 over 3. And that is what they were looking for. Okay, so the next thing we're going to do is, so let's just remind you that with related rates there are 2 handouts for the homework, and we have the bookwork. We do the handouts because the handouts are some drill and kill that will help you get used to related rates. The first handout, it looks like this. It says related rates and circles, and you can find that on the website. I'm going to go ahead and do 2 problems from that handout. Related rates and circles. I'm going to go ahead and check the, see if things are blurry. Looks pretty good. Okay, so now we're going to actually do things that have units in them, and we'll work our way to the book problems, and they'll still be kind of dumb when you do the book problems, like a square is shrinking. And then after a while we'll look at problems where 2 boats are leaving and someone's shadow is moving and an airplane is taking off, and you'll see the applications to the real world. But we have to kind of start with baby steps. And it says if dr dt equals 5 and r equals 4, find dA dt. So what's happening? A circle is growing in size. I'll draw the circle. We don't really need this picture, but we'll draw it. There's the radius. So the circle is growing. The area, circumference, and radius are denoted by A, C, and R respectively, which means in that order. Area, circumference, radius. Time is denoted by T. So they're asking us to find dA dt, and they give us some values. Remember, that's a variable. Dr dt is 5. R is 4. They want us to find this variable, dA dt. Well, I know there is a formula for the area of the circle, and so this is something we're going to have to memorize. The area equals pi r squared. Now, in that equation, there are only 2 variables, the area and the radius. Pi is a constant. So what I'm going to do is I'm going to go ahead and differentiate both sides with respect to time. And you'll see that, I'm going to end up getting a dA dt, so let's, derivative of A is 1 times dA dt. The derivative of pi r squared, well, remember, pi is a constant, so the derivative of r to something is 2r. So this is 2 pi r, and then we're going to write dr dt. Okay, so we have some things that we can plug in. R, we're going to put a 4 there. And this variable right here, dr dt, is 5. We'll put a 5 there. Let's see what it gives us. dA dt is 2 pi 4 5. Now, if I was a purist, I would be writing all the units. I'll write the correct units at the end. So this is going to give me 4 times 5, 20 times 2. So this is 40 pi. Now my units, I have to put area on the top. So the area, and we're looking at feet here, so we're going to say the area is feet squared over the time that we're using, and in this example, it looks like it's seconds. Notice that's what we have here. The radius is measured in feet, and the time is measured in seconds. And so we've just done our first real related rates problem. Let's go ahead and do another one. Problem number 7. The same thing, a circle is growing. I'll draw the circle again. In size, the area, circumference, radius are denoted by A, C, R respectively. Time is denoted by T. We have dc dt, that's the circumference changing, is 7. Circumference is 6. And they want us to find dA dt. So let's go ahead, because we have to find dA dt, I'm going to write out the area of a circle, pi r squared. This is going to look very similar to what we did before, but repetition will help us get this down. So, I take the derivative and I do what I did in the last problem. dA dt equals 2 pi r dr dt. Okay, so we have that written down. So what we can do is we can say, look at this. Circumference is 6. Oh, wait a minute, there's no circumference there. Let's say the dc dt, change in circumference with respect to time, is 7. Oh, okay, so I still don't see that circumference there. I need another formula for this circle that has their circumference in it. The circumference of a circle is 2 pi r. Now I'm going to differentiate both sides of this equation with respect to t. And notice when we do this, we haven't had the equation have a t in it. The t's, these are all functions of time. We don't have any t's in this equation, but you'll see the t pop up in our derivative notation. So the derivative of c is 1 dc dt. So I'll write dc dt. This equals the derivative of 2 pi r is 2 pi, and then we have to put a dr dt. Okay, so we have this, but look at this right here. We can put a 7 there, and that's great, because that will give us a dr dt. So let's put a 7 here. And we'll solve for dr dt because we need it right there. We need a new color. So we need that guy right there. So 7 over 2 pi equals dr dt. So look at this. This is great. I need yet another color, and I think I'll use red for the radius. We need that guy right there. We could have done this earlier maybe, but how do we find the radius? We'll take this right here, circumference equals 2 pi r. We know the circumference at that time is 6. 6 equals 2 pi times r. So this is just by plugging the circumference into this equation, circumference equals 2 pi radius. So it looks like my radius is going to equal 6 over 2 pi. Radius equals 3 over pi. And so there we have that. Now some teachers would say, solve for dr dt here, without putting the 7 in, and then plug it back there, and then you can plug some values in. But I've thought about this a lot, and I think this is the simplest way. And using colors certainly helps. The green, we never, I haven't really been using colors nicely, but look at this. This is where we use the circumference of 6 to get the radius. Okay, dA dt. This is the change in the area with respect to time. We have 2 pi. The radius is 3 over pi. We see that right there. And dr dt is 7 over 2 pi. Okay, the 2 pi's can cancel. And it looks like my final result is 21 over pi. This is area, and this is time, so it's going to be feet squared per second. And so this right here is related rates and circles. One of the 2 handouts that you'll be working on for your homework. There is another handout. We'll only do one problem from this handout. It's called Related Rates and Right Triangles. Related Rates and Right Triangles handout has 9 problems on it. And it looks like that. And that's on the website as well. Let's go ahead and do this problem. A right triangle is changing in size. The area is denoted by A, the perimeter P time T. So here's problem 1. It says if y is fixed at 4 feet, so this right here, go ahead and put a 4 here. So this triangle is changing in size. We'll see some applications of a triangle changing in size, like the airplane taking off and some other examples. Right now, there's really no connection that we're making to the real world, but we want to work on the math before we can do that. So y is fixed at 4. dz dt is 21. X is 3, then find, whoa, look at all that. So we're supposed to find dx dt, dA dt, d theta dt, theta, that means there may be some trig, dp dt. Okay, so let's do the first part where we're trying to find dx dt. This may take more than the space I have on this paper, so that's alright. So we say, is there a formula that we can write that has, an x in it? There's a few of them, but we are also given that dz dt is 21. So maybe we want our formula to have a z in it as well, and we have a right triangle, so maybe we can go x squared plus y squared, which is really 4 squared, equals z squared. Okay, what I'm going to do now is I'm going to differentiate with respect to t. d dt. Okay, what is the derivative of x squared? 2x dx dt. The derivative of a constant, I mean, I could write 16 there, but I'm taking its derivative, it's going to be 0. And the derivative of z squared is 2z dz dt. Okay. Well, now we are using the Leibniz notation. We don't want to just put x prime there and z prime there, because now we have lots of variables and we don't want to forget what we're taking the derivative with respect to. Notice there's a 0 there and each term has a 2, so we'll multiply the equation by 1/2. When we do that, we end up getting x dx dt equals z dz dt. Okay, now I can solve for dx dt. I'm just going to plug the values in. I have dz dt is 21. And it says x is 3. Now, this triangle is changing in size. So, you know, when x is 4, things are going to be different. But it said x is 3, so I'm going to go put a 3 right here. And the other letter that I need is z, and it seems like, I don't know what it is, it didn't give me z. But what you can do is you can say, look, I can find out what z is by plugging that into this x squared plus 4 squared plus z squared, because we know x is 3, so this is 3 squared plus 4 squared equals z squared. That's 9 plus 16, 25 equals z squared. Square root property is going to tell me that z is plus or minus 5. Z is a positive number. So I'm just going to jump right to z is 5. And so we have that right there. So we'll go ahead and plug these values in. We have x is 3. We have dx dt. Z is 5. And this orange thing, dz dt, is 21. So dx dt is 5 times 21 over 3. The 21 and the 3, oops, that was the wrong way. They can reduce to 7 over 1. So it looks like dx dt happens to be 35, and it describes the change in that length there. So we're going to put the length of x, you know, what that's measured in, over t, which is seconds. So this is going to be feet per second. And so there is our answer for the first part. So this problem here is really, it looks like it's 4 problems in one. But it's going to help us big time. The next one we want to find, so I'm going to cover up some of this work, is dA dt. Maybe you can do that one on your own. Okay, dA dt, that stands for the area. Do we know the area of this triangle? The area of a triangle is 1/2 base times height. It's a right triangle, so it's going to be 1/2. Here's the base, here's the height. So the area is 2x. What are we trying to find? We are trying to find dA dt. So we want to differentiate both sides with respect to t. This is going to be dA dt. That's what we're looking for. The derivative of 2x is 2. And then we have dx dt. Okay, so there are two variables in this equation. We're trying to find dA dt. All the conditions are the same, and I believe we have found dx dt, which is 35. Let me put that right here. dx dt is 35 feet per second. So I'm going to circle that. I don't even know if you can see that. I'm going to check. Yeah, you see that yellow there. Circle that in yellow, and that's what we're going to put right there. Okay. So this is going to be dA dt equals 2 times 35, which is 70, and we have to get our units correct. Maybe I should put this here. dA dt is 70 area, and we are working in terms of feet. So this is 70 feet, square feet, so we'll say feet squared per second. And so that is what we get for dA dt. Now the scary one. The scary one happens to be d theta dt. That's what we're looking for. Okay, so do we know any formulas that have a theta in it? Well, we can say the trig ratios, and there's 6 of them, but we probably want to incorporate one that has this constant 4. And so maybe the one we have the opposite. There's a few ways we can go on this. I'm going to go with the sine. Sine of theta, Oscar had a hunk of apples, is opposite over the hypotenuse. So that is what we're going to use for that. Let's go ahead and write this sine theta as 4z to the negative 1. I'm going to hit both sides with the derivative gun with respect to t. The derivative of sine is the cosine. Now this is going to feel strange. Now we have to hit this with, we have to multiply this with d theta dt. On the right hand side, we're going to do the power rule, and this is going to give us negative 4z to the negative 2 dz dt. Okay, I'm going to move this up a little. We might have to move it back. We have cosine theta d theta dt equals negative 4 over z squared dz dt. Okay, so dz dt was 21. Z, and I think we actually found that. Wasn't Z 5? Let me put it up here. Z is 5, and we were using blue for that. So we know what to put here. D theta dt is what we're looking for. Oh, we're supposed to find the cosine of theta. So the cosine of theta happens to be Oscar had a hunk of apples adjacent over hypotenuse. That's x over z. Okay, oh man. Let me just write this all out again. And we'll circle the things in the correct colors. We do have 1, 2, 3, 4 variables, and we're trying to solve for the one variable d theta dt. I'll go ahead and circle some things again. And then z is there. Z's blue in this problem, and x in this problem was green. Get the feeling that I'm running out of colors. Did I use red yet? Not in this problem, so in case I need another color, I have red. Let's go ahead and plug these numbers in here, and we're kind of covering up that. The dz dt is 21. X is 3, so I'm going to move this up so you guys, we don't cut you off here. So this is 3/5 d theta dt equals, this is multiplied, -4 over 5 squared, 25. There's the 21 there. Okay. And then we have times the orange thing, which was, we said it was 21. Okay. So we're almost done with this. We're trying to solve for d theta dt. I'm going to multiply both sides by 5/3. So I have d theta dt equals -4 over 25 times 21 over 1 times 5/3. Okay, so we have 5 goes into both of those, and the 21 over 3 is 7 over 1. Looks like my final answer is going to be -28 over 5 d theta dt is -28 over 5. Now, before I box this answer, we know that time is seconds. What is the angle measured in? Well, the angle, we didn't mention anything about degrees here. So radians is actually what we're going to be using for the angle. So this is going to be radians per second. And that is our answer for d theta dt. Okay, I believe we have one more to solve for, and so problem number 1 on this was 4 problems in 1, but the more of these things you do, the better you get at this. The theta one was pretty traumatic because there was a cosine and a sine. Okay, so the next one we want to do is dp dt. Put that right here. This one's not going to be as bad. So dp dt, and I want you to try to do this one on your own. Pause it. P is for perimeter. You have to ask yourself, do you know the perimeter of that triangle? Find this and put the correct units. Okay, so the perimeter of this right triangle happens to be, it's just taking a walk around that triangle. It's like if you were a little bug and you were going to walk along that triangle. Oh no. Ah, hey, whoa, knock it off. Got it. And so, perimeter is x plus 4, so we're walking around that, plus z. Okay, I want to go ahead and take the derivative with respect to t. This is dp dt equals the derivative of x is 1, just like the derivative of p was 1, so this is dx dt. The derivative of 4 is 0, and the derivative of z is dz dt. Okay, I'm trying to find dp dt. I've got dx dt. We used yellow for that one. And this one right here is blue. Ah, it wasn't blue, it was orange. Okay, so, like I said, oh man. Oh, what am I doing? Okay, might as well just get some paint out here. It's right here. Seeing me do this crazy thing with the whiteout is making you realize how lucky you are. You don't have to come to class and bear with that. The craziness of me in class. You can just see it from a distance. Look at that. Okay. It's orange there. Let's go ahead and put the values in. dp dt equals 35. I'm not going to put the plus 0. And then we have plus 21. I can do that without a calculator. 100. Man, I just keep messing up today. 56. And our units are, let's see, perimeters measured in, oh, that's just measured in feet. And our time is seconds. And so let me take a look at what we have here. This is part 1 of related rates and right triangles. It should allow you to do both of the handouts, the one with circles and the one with right triangles. It will also allow you to do problems 9 and 10 and maybe 5 and 7 for the bookwork. So when I come back, we'll do part 2. We'll break this up into 3 parts, and part 3 will be the one where you have boats or airplanes or people with shadows, and that's how we'll do this. You guys take care.